Ladies and gentlemen, my name is Jan Horacek, and on behalf of all my colleagues, I would like to present you fast ELM temperature in compass and tokamak jet divertors. First, motivation for fast ion and electron temperature measurement during ELMs is shown here. It's pretty clear that tungsten sputtering strongly rises with ion temperature, and that's why it's dominated by ELMs. It's clear from this tungsten sputtering graph as a function of ion energy, where it strongly rises, at least for deuterium, that it can sputter the tungsten. And if we increase the energy of deuterium ions by a factor of 2, we get stronger sputtering yield. And this cannot be directly measured, the ion temperature. However, we can measure the electron temperature on the divertor by ELMs, during ELMs by probes. And it has been measured, in fact, that it's much lower than electron temperature on the pedestal. This has been, in fact, measured in those three publications in 2015, 16, and 18, that the temperature drops from 1 kilo electron volt down to 50, or even lower, down to 6 electron volts on the divertor during ELMs, and which in fact implicated, which was interpreted that electrons transfer their energy into ions by just parallel electric field by this free streaming, according to free streaming model, collisional, and that's why it implicates very high ion energy, which can sputter the tungsten. And so, in fact, outline of my talk is that we questioned this measurement. In 2020-21, we performed bit1 simulations where we, in fact, observe in the code that the electron temperature on the divertor should be during the ELMs about half of the pedestal, not only a couple of % of the pedestal. And this has been, in fact, found consistent with compass observations and collision-less free streaming model, where only 1/3 of the energy can be transferred at maximum. And that's why we reanalyzed data during ELMs on jet, and we found that they are much higher than what has been published. And that's what I'm going to show you. So first, let's start on compass, not on jet. Tokamak divertor, where we have the advantage that we have two types of probes. We have either normal swept Langmuir probes, and also array of ballpen Langmuir probe array, which in fact allows to measure with 1 microsecond resolution the electron temperature just by a difference between floating potential ballpen and Langmuir probes. And this allows us to measure filaments during each ELM. And we see that temperature at the maximum, what we can see, so during ELM filaments, reaches nearly 100% of the pedestal value. This is the pedestal value, that's what we see on divertor. So on average, it's about 80% what we observe. And according to simulation, it should be like about 2/3 of the pedestal, so 200 out of 300 in the pedestal. If we take filaments, if we take the whole ELM, which is kind of longer in time, it drops to about 30–40% of the pedestal values. So in fact, this is consistent with the free streaming model, which is collision-less, so only parallel energy can be transferred from electrons into ions. And so these are consistent with the measurements. So the question is whether on jet is any different. So we used exactly the same conditional averaging technique, which was applied on jet during ELMs. So this is pretty simple. We identify each ELMs by beryllium line on jet or by d-alpha line on compass. And we have to identify very precisely what is the time equals 0 of the ELM itself, what's the peak maximum. And at the same time, we sweep the voltage and we measure the current. So in fact, every ELM can in fact generate in voltage current characteristics can generate 1 point. 1 point corresponds to each different ELM. So here we have about 300 ELMs in this case, many discharges combined all together to get enough statistics. And like this, we can reconstruct IV characteristics every 1 microsecond conditional averaged. And the question is whether this characteristics is credible, because in fact here we have to assume that all the ELMs are identical, that in fact that the frequency in fact in such a case doesn't matter of the sweeping, but it's only a question of the data acquisition speed. So the identicality of all the elms is questionable, and that's why we did it on Compass, because on Compass we can directly cross-check this measurement, which is shown here in time. This is dozens or hundreds of microseconds in this case, the blue and black line, depending whether we use 3 or 4 parameter fitting. This is from the swept probes, conditional average, and then compare with this violet dots. Every dot comes from different elm, a different filament every 1 microsecond. If we average all these purple dots, we get this red line, and you can see that it's very well comparable. In other words, it means that if we measure it fast using the ball pen Langmuir probe array, we can see more or less the same value at the peak maximum, about 100 eV. The pedestal was around 300. We can see the filaments go up to the pedestal, but the conditional averaging value goes about two-thirds of the pedestal in this case, a little bit higher than the mean value of the filaments. Of course, this technique in principle must underestimate the maximum value because, of course, all the events, the filaments don't match exactly at the same time, but they correspond pretty well. In other words, our conclusion is from Compass that the conditional averaging technique is quite credible, at least below 100 eV, because that's the limit given by our voltage. And of course, it must, in principle, underestimate the maximum temperature on the divertor, but only by a factor of 2, not more than this. Now we are going back to jet divertor. First start with simulations, bit 1 simulations by David Sakaya, where particle and heat source goes to the scrape-off layer during the ELM. It goes to inner and outer divertor. We increase in such a way the source and heat terms in the simulation. We also had there some neon impurity, but in this case it was not important. It was just these simulations were used for different purpose. In fact, the neon drops the inter-ELM values, but not the ELM itself. So we could use it for our purpose. And here we see that the ELM temperature goes from roughly 0 up to about 70% of the pedestal temperature, which in fact is these 2/3 at maximum, which we predict according to collision-less free streaming model. So this is in strong disagreement with the published jet conditional average measurement, which shows much lower values than on the pedestal. So that's why we reanalyze them in exactly the same way. And this is what we get. Here you can see every 10 microseconds, which is the data acquisition speed of the jet Langmuir probes. We sweep the probe and do the conditional averaging, and you can see that we are now approaching the time equals 0. The beryllium line goes to its maximum, to the peak. You can see very nice IV characteristics. Each data point comes from a different ELM, so it's a pretty credible fit. And in this case, we saw temperature about 120 electron volts at maximum, because the published value was 25. So we clearly see something much higher, which is quite close to half of the pedestal temperature, which was 240 eV. This was one probe near the strike point. There are a couple of other probes. So in fact, what I'm showing you on my next slide is always the probe which has the highest temperature which we could measure. So not only in time, but also in space, we are looking for the maximum value. Let's go for the next slide. Before going the last slide is I show you that there are pretty a lot of problems with the conditional averaging on jet. We could analyze only 60 out of 72 shots because there are many probes which are damaged. They are near the strike point, especially those probes. Then the strike point sweep in many such cases where in fact the temperature was reported below 10 electron volts. This is shown here that it just the strike point sweeps here, and you cannot then assume that all the ELMs are identical. They are, but not on one probe, of course. Then there are too few ELMs in many cases. Then there is quite a lot of noise for ELM detection. We have to match all these ELMs together in time to really synchronize them. And also many of them are unfittable because the voltage is too low. And this is my last and most important graph. Is a summary of all ELMs on jet. Here you can see the pedestal temperature in logarithmic scale, and this is the divertor temperature which we measured. So those purple values are those which has been published. Those crosses are very low values like 10 eV or even lower on divertor, but I claim that they are unanalyzable because of those problems which I reported here. Then those triangles, they are analyzable, but my values are much higher by order of magnitude or even 2 orders of magnitude in some cases. So for all those which have very high pedestal temperatures, I see temperatures which are higher than 200 electron volts for at least 20 discharges. In fact, for those cases, I can only say that it's at least 200 EV, because in fact, in this characteristic, I can see just a straight line, which means that the temperature is just higher than 200 EV and you don't know how much it is. But for us, it's important to know at least the minimum value. And this is quite in accordance with the simulation, which is here shown by the green line, which is about 50% of the pedestal temperature. For those values which are here in strong black color, correspond that they are pretty well credible, and they have also very small error bars according to the conditional averaging method. And so those are not very credible, those with white color. So for low pedestal temperatures, I can say that we have pretty good match with the published data, but for those medium and higher pedestal values, I get values much higher. So in conclusion, on COMPASS, we have verified that the conditional averaging technique worked pretty well, but one has to be quite careful about how to analyze this. There is many conditions which have to be satisfied for the data. The values on average are much higher than what has been published, only quite close at the lowest pedestal values. So, which is in fact good news for ITER, because it means that there is no significant transfer of energy of ions into electrons. And anyway, at this temperature region, which we are speaking about, a couple of about kiloelectron volt on the pedestal, the sputtering yield is quite close to the maximum, which is maybe the most important. So thank you for your attention. Please read my submitted paper into nuclear fusion, which I'm just now submitting.